This is Surveying 1, Lecture 2, and in here we're going to talk about measurements. Measurements is an extremely broad topic. There's a whole bunch of things that we can cover in here, and so I have a Part A and a Part B. Part A is the easy part. Part B will probably take you the entire term, this term, as well as Surveying 2, to be able to really appreciate and understand this. And so I intentionally am going to break it up into 2 lectures so that there is some time, first of all, between seeing Part A and Part B, because many of you will probably be lazy and not be reading from the book before you actually listen to these lectures, which is the opposite of what I hope you will do through the rest of the term. But the other reason is that throughout this term, I will be referring back to Part A. And what I mean by that is I will, in future lectures, well into the semester, I may refer to measurement concepts from Part B. And so I want you to know that you can go back and review that without having to watch Part A again, which I think is fairly simple. And I think you'll be able to retain this information without having to go back and look at it over and over again. So measurement. We want to start by talking about the fact that there's no such thing as a perfect measurement. The only exception to it is if I want to count the number of fingers on my hand, I can go 1, 2, 3, 4, 5, and it's not 4.9, it's not 5.2, and so forth. So counting is one of those measurement, probably the only one of the measurement functions that's where it's possible not to have a discrepancy. But if you've ever flown or you even counted the number of heads in a big classroom, you know that counting the number of heads in a plane, for example, that flight attendants walk back and forth because there's 2 flight attendants counting and they can't seem to agree on the number. So even with counting, when you get above about 5 or 10, it gets a little iffy as to whether measurements can be perfect. But certainly theoretically, measurements can be perfect. But with other types of measurements, the kind of measurements that surveyors do, there's no such thing as a perfect measurement. So you have to be resourceful. You have to draw upon principles of physics, principles of mathematics, algebra, geometry, trigonometry, statistics, probability, and so forth to be able to understand this properly. So surveyors also must be very careful in professional practice, and certainly in this class, not to say that any measurements they have made or that they report are perfect, even if you are in court and you have some hotshot attorney trying to make you feel like you are less than perfect. Because the truth of the matter is that no measurements are perfect. But this does not mean that the survey is not expected to deliver accurate results. And so a lot of what I have here in Part A is talking about how you can have those 2 seemingly opposite statements or conclusions going on at the same time. And you again need to have this in your bloodstream, because as a surveyor, even if you're not yet licensed, you need to be able to comfortably say and support and back up the strength of your convictions and the strength of your competence in being able to make measurements. And you should be able to point to what I call surveying theory or measurement theory that backs up what you are saying about your inability to deliver a perfect measurement, but that you are able to deliver a measurement that is accurate enough. Unfortunately, the surveyor is the only person who sometimes knows that little fine point and often has to make a conclusion as to what is accurate enough for a particular situation, because the person paying for the service really doesn't understand this. So we're going to start by talking about accuracy and precision. In everyday English speech, we use these terms synonymously. Sometimes we talk about making a measurement accurately, sometimes we talk about doing something precisely, and we kind of use them as synonymous terms, and many times they are synonymous. And as a surveyor, please don't be geeky. So you're going to go visit, let's say, your kid's second grade teacher, and they talk about something being accurate or something being precise, and they're not speaking about it the way that we are going to be talking about it here in a few minutes. Well, don't take them to task and give them a 15-minute lecture on the difference between precision and accuracy. It's important for me to know that. It's important for my fellow surveyors to know that. And it's really important when it matters, and only when it matters, for my clients to understand that there is a difference between those two words. But you don't go around throwing out this information just to show people what a hotshot you are. All right, so precision has to do with the fineness of measurement. So let me talk about a ruler, for example. Let's say you have a yardstick or a 12-inch ruler, and you're going to make measurements with it. Well, if you've looked at the selection of things that you can buy to make a measurement, you've probably seen the average ruler will probably have 1/8 inch increments. That's kind of the average. You get one of those free yardsticks, more than likely it's graduated in 1/8 of an inch. And you buy one of those pocket roll-up tapes, most of the tape may only be marked off in 1/8 inch increments. But if you look at certain kinds of rulers and certain kinds of tapes, you'll see 16th inch increments. You'll see 32nd inch increments. If you look at machinist scales, for example, what a machine shop would use, it's not uncommon to see 64ths or even 128ths of an inch. And to read 128th of an inch, by the way, there would always be metal scales. You pretty much have to use a magnifying glass. And you can get to smaller increments than that using special measuring tools called micrometers or similar devices to that. Today, using laser technology, you can also do measurements down to thousandths, 10,000ths, 100,000ths, even a millionth of an inch. So the fineness of measurement simply means you're getting more and more precise. It doesn't mean you're making them more and more accurate, because you have that free yardstick you got from the lumber yard or the hardware store. Well, if it was made using kind of green wood, maybe 2 years later, an inch is really not an inch anymore. It's a little bit less. And if it was cut in a weird way from the wood, maybe one part of the yardstick shrank more than the rest. So one part of it for the first few inches is consistently, let's say, a 16th of an inch short, or a 32nd of an inch short, or an 1/8 of an inch short. But when you get to the other part, it's short even a lot more. So you can have all these kinds of things happening. Even with metal scales, you probably know by now that most metals, except for some very special alloys, expand and contract as the temperature goes up and down. It's also possible, if you have a really thin measuring wire type of situation, that you can actually stretch the metal. You can deform it where it doesn't shrink back up. And even then, if you stretch on like a steel tape used by surveyors, you pull on it hard enough, you can actually stretch it. Now it'll bounce back because it actually has what's called tensile strength that allows it to come back once the tension on the ends of the tape have been relaxed. But this is what I mean about precision. This is the more you pay attention to all those things about your measuring tool, it means you're being more and more precise. So sometimes we have this term called least count, and that's what these numbers over here all represent. If you have 3 choices of measuring tools that are in 1/8, 16ths, and 32nd of an inch increments, the smallest least count is 1/32nd of an inch. So if one person measures something with a ruler or yardstick that's graduated in 30 seconds of an inch, and someone else with a ruler in eighths of an inch, or it's the same ruler, they both graduated in 30 seconds, but someone says, it's too hard to read to the 32nd, I'm going crazy counting all those lines, I'm just going to measure to the nearest eighth of an inch because I can see those are the long lines, and I just count how many there are of them because there's only 8 of those to the inch. So you could say the person who measured to an eighth of an inch had less precision in their work than the person who measured to a 32nd of an inch. Repeatability is another measure of precision. So somebody goes out and measures something, doesn't necessarily have to be a surveyor, and again it could be using the yardstick, and they measure the length of a table or the length of a room or whatever it is, and one person measures it once, the other person measures it 5 times and gives you the average. And assuming all those 5 measurements are relatively close to each other, then the average is generally a better result than the single measurement, even forgetting the fact that the yardstick has shrunk or expanded or whatever. So precision is often a reflection of the care in how you measure, or it's a reflection of the tools you are using. And so we often say precision is emphasis on the methods. Now, accuracy, on the other hand, has to do with the result. So the result is that my answer is very close to the true value compared to somebody else's result. And so we can say that one person's result is more accurate than the others because their answer is closer to the true value. So the emphasis is on results. So let me just back up again. Precision emphasizes the methods that are used. Accuracy emphasizes the results. Now this is still kind of a little abstract, so let's talk about something a little bit more specific here in a minute. But the main thing I want to make sure that you have already embedded in your mind is that precision and accuracy are not synonyms. The other thing that's really important as a surveyor to remember is just because you are being precise or striving to be precise doesn't mean you'll get an accurate answer, or the other way around, just because you're striving to be accurate doesn't mean you get a result that has a high degree of precision in it. So one of the questions I like to ask sometimes is, as a surveyor, are we striving for accuracy or are we striving for precision? Well, there's different ways to answer that. The overall answer is that our client is expecting accuracy. So the surveyor definitely has to strive for accuracy. But in terms of the methods that you use to get to accuracy, a surveyor can only do that when they are also striving for precision. So a surveyor, as I say here, has to strive for both. The thing that you need to realize that it's possible to do well in one and horribly in the other. It's also possible to accidentally do well in one and not the other. And the reason I mention that is that many surveyors are very proud of some of the results they get and think that they are really good at what it is they do. But it could easily be that they are considering one of these things, precision and accuracy, and not looking at the other. Or it's possible that they actually accidentally did well, because as you'll see here, it's certainly the laws of probability tell us that it's definitely possible for that to happen. Okay, so I'm going to go through a little analogy, and the analogy we're going to use is shooting at targets. So we have a gun, a rifle. I'm going to shoot at a target, and I'm going to show you how you might perceive these two things. So there's a shot, and we hit the target in the bullseye. There's the second shot we took, and we take a bunch more, and when we finish, we discover that, if you will, the centroid is a technical term. If you don't know what it is, you might want to look it up. but it's kind of the average position of where all these shots are is probably at the center of that yellow circle I've drawn there. Now I did that by eye, but there's a way to mathematically actually calculate that. And what I say here is that you're being very precise because your shots are tightly clustered. Your shots are tightly clustered, but it's not accurate because the average of all those shots is not on the center of this target. So I'm calling this precise. Now keep in mind, we could look at any one of the individual shots and make some conclusions as well. So we can say that maybe these two shots up here at the very top are horribly inaccurate. We can also look at maybe these 2 or 3 shots near the bottom and say, oh, these are really good. So you see how by looking at a single shot, for example, you could come up with the incorrect conclusion that the rifle or the measurement is being done accurately when it just happens to be an accidental part of the scatters that you would get if you repeated the measurement over and over again. Now some people say, well, in that case I'll only do one measurement. Well, the problem is if you only do one measurement, how do you know which one of these you've got? Keep in mind, here we have the convenience of a target to see where we fall. Unfortunately, when we are surveying, we don't have that target. So we have to imagine or do other kinds of analysis to figure out what the target is to know if we're accurate or precise. So here's another situation. There's our first shot. And yeah, it's not as good as that first shot we had on this first target. It's not horribly inaccurate, but it's not horribly accurate either. But if you look at all the other shots that were taken, it's actually the same or similar target pattern. So in this case, they're precise because they're clustered about as well as this first set was, but the average of all those shots, the centroid, is very close to the center of the target. It may not be exactly in the middle of that small red circle, but it's very close. So we can call this quite accurate, and it's also precise. And this is what surveyors need to strive for. So here's yet another target, and there's a shot. Hits the bullseye. But because we've only done one shot, we might come to the conclusion that we're being accurate. But what if I got this by standing at the target, walking whatever number of paces it is, you pick 20 paces, 50 paces, whatever. I stick the rifle on my shoulder. Maybe I use a mirror like Annie Oakley supposedly did, or maybe I don't. I just pull the trigger. Not a very precise method, except for people who are maybe like Annie Oakley. And yet I got an accurate result. So the point here is it's possible, in the grand scheme of things, to have an accurate result, but it's not precise. Because if I kept pulling the trigger, probably a lot of my shots are going to completely miss the target. So horribly imprecise, but we do have those occasional periods of brilliance where we actually come very close to being accurate as well. And then finally, over here, on this target, there's our first shot. It's over here, so that's pretty bad. I mean, that's even worse than our worst shot out here in this first target. Our second shot is not a whole lot better. And we go, oh, they're probably not even looking at the target. Oh, there's a third shot that's closer, and here are all the other shots. And when we finish with this and we take the centroid, we discover an interesting thing. That the average of these shots all come out to be very close to a result that's similar to this middle target. And yet they're scattered further, so they're less precise, but still accurate. And so it's possible, it's very possible, in fact many surveyors do this, because they don't all have instrumentation that all has the same precision, but with the right techniques, they can arrive at a result by averaging their results that gets the same result in terms of accuracy as what they had over here. In fact, one of the hallmarks of a good surveyor is to actually look for the randomness in their measurements, and if they get randomness, as long as they're averaging them, to be able to say, you know, I'm feeling pretty good that I'm doing a good job here because I'm getting some true randomness in my results. And then finally, just for grins, I put this set of shots up here. You see they're even more tightly clustered than all these other shots. But where's the target? So these are a very tightly clustered set of shots, but they totally missed the target. We don't even know where the target is in this case, in the case of these shots. So this is ultra precise, ultra precision, which unfortunately is the situation many surveyors today perform, especially because they don't know the techniques of analysis. They don't understand how probability and statistics works into things, and they don't understand their technology. So this could be very similar to a situation where a surveyor goes, or the target shooter goes out and buys one of the best rifles they can find in terms of all the component parts, the way it's machined, the way the interior of the barrel is grooved, maybe even the kinds of bullets that they use. And they have a super duper scope, but it's not bore-sighted. So they're taking very careful aim and getting really good shots. Maybe they even improve their precision. Again, this is a tool, right? So one of the ways to improve precision is mount the rifle on a tripod and improve your precision. But just because you improved your precision doesn't necessarily mean that you improved your accuracy. And this is one of the things that a lot of surveyors do. They often buy higher priced equipment because it is rated as being at a so-called higher accuracy, but then because they don't apply it to the job properly, the job at hand, they wind up with very precise data, but that is maybe not very accurate at all. All right, so I want to talk about errors in surveying. There's two kinds of errors, and you definitely need to keep these two separated in your minds. You're going to run up against this again and again and again in surveying 1 and surveying 2. So the two names that I want you to primarily remember here are random errors and systematic errors. There's yet one more term here that I'll talk about in a second. So random errors also have older synonymous terms that you'll see in some older books: compensating error or accidental error. Accidental error is a really bad term, and so I prefer not to use it at all, but you might run into it when you read books, not just on surveying, but other topics as well. And then we have compensating error, and I'll talk about that here in a second. So get to the next bullet. Random errors are plus or minus, so you could make 3 measurements, and sometimes those measurements are a little bit short of the true value, and sometimes those measurements are a little bit long in the true value. So we actually have an equation that the error is equal to the measurement minus the true value. So if the error is equal to the measurement minus the true value, we can have a positive error when the measurement is larger than the true value, and we can have a negative error when the measurement is smaller than the true value. The point here is that we can have a plus error or minus error, and we never know. And it also varies in size. So the size of the error, the size of the miss also varies. And that's why it's random. It's truly random. It goes all over the place. And that's one of the reasons it's sometimes called compensating, because if we have several measurements, we're making end to end. So over here, we're measuring a certain distance with a yardstick, with a 100-foot chain. It doesn't matter what it is. And that's called these the true lengths. But because of various uncertainties, our first measurement, use a different color here. So our first measurement falls a little bit short of where I've drawn the black line. The second measurement falls a little bit long, so it winds up hitting where the black line would be very close because the two errors were not the same in magnitude, but they were opposite in sign, and so forth. So you never know exactly where you're going to fall, and so you have this condition that you sometimes need to really think about so that you can effortlessly apply some of these principles. The other thing about random errors is that seldom are they large. Now, that all depends on whether you're a statistician or a surveyor. A statistician would say a large error is simply a large error. It's still random. And we say in surveying, if you have a large error, then it probably is not an error that we want to tolerate in our work, and we should be throwing that measurement out and repeating it. And we'll cover that here in the next couple of slides. So that's random error. So that's like the dividing line right here between the two types. So that's the other thing I want to just mention, that these are the types of error. Then we have systematic error, which in some older books is sometimes referred to as cumulative error. But this is the other term I want you to remember, the word bias. Because when you read books and papers on surveying and surveying science or measurement science, it's not uncommon to see more and more papers where they'll talk about bias in the measurements, and all they mean is that there's some kind of a systematic error in the measurements. So I gave you the example of the yardstick that's a little bit short per inch or a little bit long per inch. That would be a systematic error. Because every time you make a measurement with this yardstick, it simply repeats. It repeats with each measurement or unit of error. So one of the things we'll be talking about, even though many of you will hate this, you will thank me at some point long after this course is over, and that is the fact that a steel tape, if it is uniformly warmed up, all of a sudden becomes 3 or 4 hundredths of a foot longer than its nominal 100-foot length. And then what we say in a case like that is that the systematic error is proportional to the distance measured with the tape. So if the 100-foot tape is now 4 hundredths of a foot long, we can safely assume at the 50-foot point that it's 2 hundredths of a foot long, that the error is directly proportional to the measurement that is being made. On the other hand, some of you may know about this technology. I'm not going to go into it in detail. We'll eventually get to it. But you have something called prism constant error. So you have a total station or electronic distance meter on a tripod, and you set up over this point, and you have, let's say, a prism pole over here, and you have a prism mounted on the end, and you make this measurement. Now it turns out that this glass over here has an error associated with it, and you program your electronic distance meter part of your total station, if that's what you're using, to remove that error that's already in there, that's kind of inherent in the glass. It's part of the physics of the technology that we're using. And one of the most common prism constants that exists around there is minus 30 millimeters. And so what it means is that you have to correct every measurement you make by 30 millimeters because you're measuring 30 millimeters too long. And so you subtract minus, or you take out 30 millimeters from the measurement that the core technology has, and then report the distance. So in a case like that, it's still a systematic error, but it doesn't matter whether you're measuring 10 feet or 10,000 feet, you still have the 30 millimeters of error. And that's why I say it repeats with each measurement or unit of measurement. So in the first case, the steel tape, it's per foot essentially, whereas in this case, with the prism constant, it's with every measurement. And so I end by saying this kind of error can be removed. In fact, it can be removed almost entirely if you know enough. And what do I mean if you know enough? Well, I don't mean about whether you know the theory of the instrumentation What I mean is whether you know enough about the situation under which you're measuring. So it means, first of all, you know enough about the environment, so that's temperature, atmospheric pressure, relative humidity. There may be other things that your technology is impacted by that you need to know. And the other part that you need to know is everything you need to know about your instrument. How does your instrument work? What's the physics of the instrument? What's the electronics of the instrument? What causes it to give me different results than the best possible result that we could get from it? And if you know those two things, then you can apply corrections to your observations. And that's one of the things we often do. We say an observation is simply a measurement with all the systematic errors in it. Then you reduce it by removing all the systematic errors, taking all the information you know about the environment and the instrument to create your base level measurement. Now, you can never remove it all entirely because you have this steel tape, for example. It's gone up in temperature so many degrees. You calculate that out and you discover for 100 feet that's 4/100ths of a foot of expansion, which by the way is a half an inch in 100 feet. But it may turn out that because of the way you're using the tape, maybe it's in a partly wooded area, that some parts of the tape are not as warm as other parts of the tape. And so you really don't have exactly 4/100ths of a foot, but you make the assumption that the tape has warmed up uniformly. So there's always little things like that that can affect how you can correct for systematic error. But theoretically, you can remove all the systematic error. What we often say is we can reduce the systematic error to practically zero, meaning, yeah, there might be 2,000ths here and 5 millionths there and whatnot, but we say that's outside the realm of our ability to measure those errors. All right, so now we want to talk about mistakes, because again, just like accuracy and precision, we use the term accuracy and the term error and mistake sometimes synonymously. In surveying, they are not the same. So a mistake is the same as the word blunder. In fact, I prefer the word blunder just because it kind of stands out, just doesn't sound good. But neither one of these is equal to the expression error. So an error is not a mistake. So if you write down a number incorrectly, you read the wrong number on a scale, you set up or start off or end up at the wrong point because you don't recognize, or you're not paying attention, and you set up on the wrong point or something like that. And so you have erroneous data that you work from and create a report for your client, a map or a plat or whatever it is you're going to do. Those issues are not due to errors in measurement, they're because you made mistakes. And what I say about mistakes is that they are preventable through care and redundancy. They are caused by inattention. And that's one of the reasons we have lab classes associated with Surveying 1 and Surveying 2, because we want to make sure that you understand how even if you don't do it, that there will be several mistakes and blunders committed during every lab session. And while you are learning, it turns out in practice this is still very common to have. Why? Because you either don't understand enough about your instrumentation or about the job, and you make those mistakes. So errors can be minimized, mistakes can be removed entirely. Unfortunately, not everybody is capable of detecting all their blunders. So one of the things that happens is when you have a small blunder and it doesn't make your work look horrible, then it often winds up being treated as if it's an error. And we can't tell the difference. I mean, there's no way to pick them out. You just have to have that awareness always that it might be at some point when you come back and resurvey something that you pick up a small blunder that was never picked up the first time that you did your survey. So the study and management of errors is an important part of the modern surveyor. And you, as a private practice surveyor or somebody working in government, needs to make sure that you and everybody in your team knows about these principles, at least at the elementary level, so that they're helping you reduce the errors and blunders in your survey. So everybody in the team needs to be educated to some extent. You know, one of the common things that unfortunately happens with land surveyors is they hire brand new people, don't tell them anything except what to do. They never tell them why they're doing something. And so the people doing the things that they've been taught to do, they've only been told what to do and not why they're doing it, will often make assumptions that something they change in what they've been taught is still okay because it seems to be the same thing. If they don't understand the why, that's how you start having errors and sometimes blunders in your work consistently all the time because you haven't exercised proper tools of communication. Remember that the professional is responsible for all the errors that remain in the information that's provided to the client. You know, it's not enough to say, well, my no good rod man or whatever didn't do it correctly. So something that hopefully you will get once we complete measurements part A and part B is that when we as surveyors talk about that distance is 857.50 feet, depending on context, that may be an extremely ignorant statement, measurement statement. I've seen surveyors, because I go to court very often when I know surveyors are testifying in court, and I've seen them do this. And this is an incredibly ignorant way because it convinces the judge, the jury, and the other lawyers that there really isn't anything to surveying other than the surveyor going out and getting his boots muddy. There's a lot more to surveying than doing this. And so here's what we are going to cover in part B, that an informed statement about a measurement is 3 parts. That the distance is 857.50, just like we had before, but the uncertainty is plus or minus half a foot. Remember, we never say there's 0 error in our measurements. That's impossible to do. You might say it's 0.05 feet or 0.005 feet, depending on how you can back up that statement. But that's how you do it. And then there's a third part, and that's the probability of the correctness. You say there's a 90% probability of correctness. So there are other measurement professionals who actually report their results this way. And sometimes they are also referred to as surveyors because they do surveys. But I prefer, just to make sure there's no confusion, to call them pollsters. So people who, if you will, take the temperature of a population, they seek their opinion on something. So do you think all cars should be black? Do you think all cars should be white? Do you think all cars should be purple? Do you agree with that statement or not? So it could be a simple yes or no, but it could be a whole bunch of other opinions. Political ones are very common, but it can be a whole bunch of other things as well. And when pollsters report their results, they may say something like 81% agreed with our statement. So we gave them a statement such as, do you believe all cars should be white or black? And 81% said that no other color is possible. And then what you'll see, so this is the measurement. So this corresponds, this 81% corresponds to the 857.50. But if you look at this, even like on a TV broadcast, when they talk about these results of these polls, they'll say there was an uncertainty of plus or minus 5 points or 5 percentage points in those results, meaning they only took a sample. They didn't go, let's say this is something for the whole country or the whole county or the whole state or whatever. They didn't go out and interview every person in the country. They took a very, very small sample. And as a pollster, there's all kinds of scientific methods you can do to analyze the data to see whether it's totally representative of the country, so you can feel confident saying that my result is representative of what the whole country would say if we asked every individual what the statement is. But there's always measurement error, even in the job of the pollster. And what they're saying is, if I went out and selected another sample, I feel pretty confident that the answer would vary only by plus or minus 5%. So it could be as high as 86%, it could be as low as 76%. Now, if you see this, if you hear this on the TV or radio, that's about where it'll stop. They don't actually go into it in detail. Why? Because airtime is expensive. But if you read this in print, like in a newspaper or in Time magazine or one of those kinds of things, the Wall Street Journal, whatever it is, you'll see yet another number. And they'll say that this was at the 90% confidence level. So the plus or minus 5% here is in the same units as the actual measurement. And then the probability or confidence of the actual information is 90%, meaning if I went out and repeated this thing 10 times, that 90% of the time or 9 times, I would get the same result. But there will be one time, or 10% of the time, if I did this experiment 10 times, when I might get a different result. Either the range would be different, or the answer would be different, and so forth. And this is actually true of surveying. And surveyors have a hard time defending against this truth. It's actually a scientific truth that all our data has this kind of 3 parts to it. And yet we get very nervous when some attorneys cross-examining us and saying, you mean to say that you could be wrong? And you have to say, yes, statistically speaking, that is exactly true. It's true. It doesn't matter who did the measurement. There's no possibility of having a perfect result. So to study errors properly, and we're not going to be doing that in this class, you need to understand probability, you need to understand statistics as well. But what I'm hoping that you will get are these second 2 bullets, and we'll be touching on probability and statistics. This is the part that will drive you crazy until all of a sudden one day it'll click and you'll be able to talk with your peers in surveying in a way where you're comfortable with these concepts. But you have to realize that the average of several measurements is always better than a single measurement, as long as they're all done with the same level of care. I think you may be all able to intuitively subscribe to this principle. And the other part is that design of surveys is possible with a rudimentary knowledge of probability and statistics and some of the other things I've covered here so far. Surveyors are so often accused of being totally cookbook. But the truth of the matter is that if you understand these principles, you can actually design your procedures, your practices, even the instrumentation you're going to use as part of the design to be able to achieve the results that are desired by a particular client or job. All right, so pretty much going to wrap up this lecture. I just want to point out there are other topics as well that will not be within part B, although significant figures may be, but I'm going to talk about significant figures in another lecture, as well as field notes and a little bit of something about the surveying process. The other thing I want to talk about is that in this course, there is this, what I call Chapter 24, which is the topic of the professional practice of surveying. This is a really important set of ideas to integrate into every surveying course you take, so that it's also integrated as part of your education into everything you do in the work process if you become a worker in a surveying environment or business. And that includes topics such as licensure, the requirements for licensure, what licensure actually means, something that is not talked about enough, but the ethical practice of surveying, and finally, what makes you professional? What makes you professional? How do you define professional? We all like to say that we are professional, but can we actually describe what that means? Now, those parts will be in other lectures, but you probably see elements of them in many, many lectures scattered throughout this entire term. And with that, we will conclude this lecture.